In this video, I want to take a look at this problem. This problem is very similar to a previous problem that we solved, but in this case, what we have is uh, this voltage that we are applying here to this resistance diode circuit is 10 volts, and along with the 10 volts, we have a changing voltage here, right? A sine wave added on to it, and the amplitude of that sine wave is 1 volt, and the frequency is 50 hertz. Okay, so we can try to find out the changing uh, voltage at this point for our circuit, right? So how do we do this? So the first thing that we can do is we can ignore the changing voltage. Okay, let's for a moment forget about this sine wave, and let's just focus on the DC current. So the DC voltage is 10, and if we use a constant voltage drop model, how much drop will be there across this diode? In the forward bias, you'll have a zero point 0.7 volt drop. In that case, this will be zero point 0.7, and what will be the current flowing through here? So there's 10 volts at this point, there's 0.7 volts here, so the current flowing will be 10 minus 0.7 over 10k. So that's going to be your current, and that turns out to be 9.3 milliamperes, right? Now, if you have the current, and this current is basically the diode current, and let's me write it as capital just to show that this is a DC voltage. What will be the small signal equivalent resistance of the diode? That is given by Vt over Id, right? And that turns out to be what? It turns out to be 25 millivolts divided by 9.3 milliamperes, which turns out to be approximately, I think something around 20. So it turns out to be 26.9 ohms. Okay. Well, it turns out to be 26.9 ohms because I made a mistake here. This is 0.93 milliamperes, and so this is also 0.93 milliamperes, right? Because this is the resistor here is 10k, and that's why this is 26.9 ohms. Now, what we can do is we can replace this circuit that we have here with its small signal equivalent model, right? What does the small signal equivalent model look like? It's basically the voltage that we give is the small signal, which is sine 100 pi t. We can ignore the DC voltage for a moment, right? And then we have the 10k resistor, and this diode is replaced again by a small signal equivalent resistance. So this is RT, and this is your 10 kilo ohms, and I want to find out what this VD is going to be, the small signal equivalent voltage. And what's that voltage going to be? That voltage is, so now this circuit is just a voltage divider circuit, right? So you can have VD equal to uh, this is 1 sine 100 pi t, so the voltage is 1, and then you have RD divided by RD plus 10 kilo ohms. And if you substitute the value of RD and calculate it, what you get is VD equal to 2.68 millivolts. Okay, so now what we can do is we can combine both these voltages and say, okay, what is the total voltage at the diode output, at the output here that we get? So we have a 0.7 volt signal, and along with the 0.7 volt DC signal we have a sine wave of 2.68 millivolts. So the total voltage is what? So let me write it here. So my total diode voltage is equal to 0.7 plus 2.68 sine 100 pi t. Okay, hopefully that makes sense. And this kind of circuit is something like a voltage regulator. Let me just explain how how this is a voltage regulator. Okay, to do that, let me just clear the screen a bit before we carry on our discussion here. So, okay, so that should be enough. So take a look at the input voltage. What is the input voltage here? We have 10 volts DC, right? You have a DC signal of 10 volts, and you have a changing voltage of 1 volt. So you have a 1 volt, let's call it a AC signal. So what is the change with respect to the constant signal? It's around 10%, right? So there's a 10% change over the average voltage. Now at the output, what happens? What happens at the output? At the output, you have a DC voltage of what? 0.7 volts, and you have a AC voltage of how much? It is 2.68 millivolts. I should have written this as milli, right? That's 2.68 millivolts. So now what is the percentage here? So you can see that the percentage is 2.68 by 0.7, and if you calculate that, that turns out to be, okay, this needed to be 2.68 milli, right? And to calculate the percentage, you multiply this by 100, and so we get this is equal to 0.38%. Okay, yeah, that's what I got. So so the voltage, there was a 10% deviation in the voltage here, and that deviation has been changed to a 0.38% change. So the voltage now is changing much less. And if so, where is this used? This is used in applications where you want to have a constant voltage. Okay, let's say for some reason your source is not able to give you a constant voltage. It gives you 10 volts, but it gives you a 10% variation over your 10 volts. Okay, then you say, okay, what I want is a very very accurate DC signal. So what do? I make a voltage regulator like this and get an output here. Now I don't get 10 volts here, but I get zero point 0.7 volts, and that zero point 0.7 volts is much more stable as compared to these 10 volts, and that's called a voltage regulator. So let me write that here: voltage regulator. Okay,